Hello, everyone, and welcome to the Geek Narrator podcast. I am your host, Kaivalya Apte, and today we are going to talk about Opte, which is a new query optimizer. And I'm joined by Alexis, who is the lead developer of the project, and we are going to understand what Opte is, what problem does it solve, and the internals of it. Hey everyone, before we go into the episode, I want to draw your attention to a truly remarkable news that is coming up from the Apache Kafka community. This is going to change the way we think about data streaming with Apache Kafka. We are talking about KIP 1150, and this is not just another feature in Apache Kafka, but it's an entire paradigm shift, bringing in the object storage optimization within Apache Kafka reference implementation. It's not outside Kafka, it's all within Kafka. This is driven by the need to make Kafka more cost-effective when it comes to cloud environments. Now imagine the possibilities where you can get rid of inter-zone data transfer costs and also local disk usage. Aiven, a fantastic partner of this channel, is at the forefront of leading this exciting development. If you want to know more, I highly recommend you read more details about the KIP using the link below in the description. You will learn about the proposed changes, the motivation behind them, and the future of Diskless-topics. I want to thank Aiven for sponsoring this video and supporting innovation within the Kafka ecosystem for the greater good and not just for profit. I hope this ensures that Kafka remains the leading data streaming engine. Now let's get back to the episode. I hope you enjoy. So welcome, Alexis. I'm really happy to have you here. Thanks for joining me. And let's start with a little bit of introduction about yourself and about your journey and what you've been doing these days.
Hi, KV. Thanks for having me on the show. It's a real pleasure to be here. I'm very excited to talk about Opti databases and core optimization in general. So my official title right now is a system programmer in the computer science department of Carnegie Mellon University, working with the database group. Like you said, I'm currently the project lead on the Opti Core Optimizer, where we're kind of rebuilding the new generation of Core Optimizer that is more explainable, more extensible, more adaptive, more performant, and a bunch of other characteristics, which I'll be happy to dive into. So I originally joined the Opti project about a year ago, while I was still a master's student at Carnegie Mellon. But only took it over and rebooted the entire development process around 3 months ago, where I joined CMU as a full-time staff in the database lab.
Perfect. Yeah, that's so cool. And yeah, as you said, there are like different problems you wanted to solve, like extensibility, performance, and optimization, and there are a bunch of features that we are going to talk about. And I'm happy to go as deep as you like in all those topics. And also, I want to thank Andy Pablo, who kind of introduced me to you, so we are able to record this podcast. So thanks, Andy. And as we were discussing before the recording, right, we want to typically start with the problem space, understand it a little better. So not to assume that all our viewers would understand like what query optimization mean, right? So let's take a step back and try to understand what is the problem space, what are the gaps in existing solutions, and why was Opti created?
Yeah, no, absolutely. So before getting into what a query optimizer is and how it gets defined, because it's a really broad area, like query optimization in general just touches many things. Let's first talk a little bit about how what led us to developing this project. So why should we care about database query optimization? So nowadays, databases have really become ubiquitous, right? More than ever before in our history. And I mean this both in a sense of like individual systems have grown to a scale that's like unimaginable even like 10 years ago. Systems like Redshift, BigQuery, they process millions of transactions a second. But also we are assisting to an explosion in the number of databases vendors out there, right? So if you jump back like 20 years ago, one of the first decisions that you had to take when you wanted to build an application was, what database you want to use. And back in the days, well, it wasn't that complicated. You just had to choose between like Oracle, MySQL, SQL Server, Postgres, these big players. And you would just go to, whoever gave you the best support, the best deals. And it was fine because the applications were not that specialized, as opposed to what they are right now. Um, Over the last decade, we've really assisted to like the rise of like analytical databases and also transactional databases. Like systems have grown in scale. So the abstractions that were provided by these old database vendors, which was kind of like this one size fits all solution, is no longer sufficient for most applications. This is why we've seen, so many new commercial and academic databases designed for specific workloads. So 10 years ago, there's also like this other big revolution, which was Snowflake, right? Which was disaggregating the storage layer and the compute layer. And this is really a big thing, right? Because even though your workload might change, um, your storage, your data remains physically the same. And this means that you no longer need to tie your storage with, whatever database vendor you choose. And that's why we've assisted the last 10 years to a rise of many specialized compute engines, right? And in some sense, it was like the low-hanging fruit to optimize your workload, right? So if you had a specific need, for example, like in graph traversal, right, you could use an engine that's specialized in like precisely that. And that's what we've seen with like analytical databases in general, which we call OLAP databases, right? We've seen the rise of Velox, Data Fusion, Spark, DuckDB, to such an extent that these systems have pretty much become commodity in the space. So circling back to your original question, what database should you use today, right? What makes one database better than another? And here at Carnegie Mellon, we believe that there's kind of two differentiators, which will, in the future determine what database is better than another. The first one is going to be user experience, which is pretty much like how well is the database integrated with like your application? How quickly does it auto scale, for example? How easily does it auto scale and all these things? And then the second criteria, and this is where we get into core optimization, is how well can you use your existing hardware, right? So you have a specific engine. Now, how well can you actually utilize this? Core optimization is not new, but we believe that it is about to become one of the, if not the most important components in databases, for the foreseeable future. And this is because compute is no longer going to bring you that many more optimizations. And this is because, we've reached some hardware limitations with, the end of Moore's law. But also because, like I said, all these compute engines have pretty much become commodity at this point. And how important are core optimizers? Like I said, you can get very different results and performance within the same system if you tune it differently. And in practice, this can translate into plans that are 1,000 times slower, right? And this kind of motivates this, right? We believe that the future competitive edge in databases is going to come from smarter optimization, getting more out of the existing hardware rather than just putting more hardware at it, or just coming up with new ways to like store your data, or new ways to execute on it. We've kind of like reached limiting gains on that front. So I don't know if you have anything to say. Otherwise, I can jump into like how we define core optimization.
Yeah, I think what you've said is a nice summary of the all the traditional databases, how they have been working, and what problems did they specifically solve, how the trend has been growing of specialized databases. But we have reached a limit, right? And then the idea is to go deeper and understanding where exactly we can get more out of the current hardware than changing, let's say, the storage layout or changing the way hardware is laid out, and so on. So I think the problem statement is pretty much clear, that identifying opportunities to optimize further and get more out of the existing hardware or the
Exactly.
existing databases. That makes sense. So yeah, I would love for you to go and explain what a query optimizer mean, and
Mhm.
also the existing gaps, right? So we said that there are gaps in the existing systems. What are these gaps, and where do they stem from?
Yeah. So let's start with core optimization. How do we define this? Um, our focus at Carnegie Mellon right now is on cost-based core optimization and plan transformation. But I want to be very specific. I mean, I want to be very clear that when you're talking about optimizing a database, you can also we can also talk about adding some indices, or read, like you said, changing the way you lay out your data, right? But one big axis that we want to focus on is plan rewrites. So when we define a query optimizer, it's this piece of software that's going to transform an input logical plan. And so the way we define logical plan is pretty much the relational algebra that you get pretty much your SQL query, right? That you input, and the database needs to pretty much transform that logical plan into something that it can execute, right? Just like you have a compiler is going to take source code and then transform it into something that it can actually execute. So the same thing happens for a database optimizer and a database planner. So the catch is that for specific logical plans, or for a specific intent, there might be, there always are a bunch of different implementations, a bunch of different physical plans that the optimizer can produce. And these physical plans can have various, execution times. Very, very, like, it can be drastically different. We're talking about factors that can reach like 10,000. You can get like the same plan that's 10,000 times faster if you optimize it properly. So the canonical example of plan rewrites and core optimization is, for example, reordering, right? So let's say you have two tables that you want to join, table A and table B. Well, you can write some rule and then swap A join B to B join A, right? So these two plans are equivalent, but depending on the cardinalities of table A and table B, you can have an execution time that's widely different across both plans. So the goal of an optimizer in practice is to kind of find this optimal plan, right, from a set of plans. So for this, you kind of, if we define it formally, a core optimizer needs two components. The first component is what we call a cost model. So a cost model is pretty much this magic function that is going to output an estimated cost. For example, the execution time, the estimated execution time of a specific candidate plan, right? And then you also need some component that's going to generate a bunch of alternative plans, right? And that's what we call the search process.
Mhm.
And both of these components are very big research problems, right? They're very hard to get right. So I can maybe start with the search, the expression process.
Mhm.
So historically, this has started like in the 70s with System R from IBM, which was this first relational database system. And one of the challenges they face is like, how do we know in what way we should order our joins? And how can we also leverage like interesting properties of our data? For example, if we know that we have a table that's already sorted, like, and we're scanning and we need the data to be sorted, we could just scan from that table directly, right? And so in the 70s, we started seeing, a bunch of algorithms that kind of try to explore the search space in a smart way, such that you do not end up with exponentially many combinations that you have to consider.
Mhm.
And so the way they do this is by just splitting up, the optimization process into a bunch of subproblems, and then you apply some bottom-up dynamic programming algorithm, and you optimize each subcomponent, then assemble everything together, and then you get your final optimized plan. In the case of System R, it was the join ordering. However, the problem with System R was that it was restricted to what we call left deep joins. So you couldn't get like what we call bushy joins, or like it was pretty much missing on certain alternatives, which is why in the 90s we saw the appearance of top-down exploration algorithms, which has been adopted by SQL Server, and now it's commonly called, the Cascade or the Volcano framework, right? So it's this almost mathematical, algorithm that specifies how you should explore and enumerate all your plans, and how it kind of integrates within a database system. Because you cannot just copy paste, the existing algorithms that the compilers people would use, because uh, we database people, we have, we need to deal with properties, for example. We need data to be sorted. And these things do not necessarily make sense for compiler people, right? So these cascades and volcano framework have become widely popular, and they've been adopted by many database vendors today, CockroachDB, SQL Server, and also Calcite, right? So Calcite is this very interesting optimizer framework, um, where you can pretty much, if you build a database engine, you can, and you don't want to like write an optimizer from scratch. Well, you can inherit a bunch of rules from Calcite, and Calcite is going to do this exploration process, like I said, the first component of a database optimizer, and it will do the costing for you as well. And you can even replace how you do that costing. So you can plug in your own cost model, and you can kind of like get the benefits of crop optimization, meaning exploration of all the possible joins and stuff like that, without actually having to write a query optimizer from scratch, which is a very, very hard problem. So the goals we have with Opti, they're multiple. It's kind of like revisiting this the way we do query optimization. So first, in terms of how can we address the limitations of Calcite, and I'll get into that a later stage. But also, these algorithms that I've specified, like Calcite, Volcano, these old frameworks, they come from the 90s, right? And they have not changed that much. And I think it's about time that we dive into these algorithms again and ask, can we do any better? Can we explore the search space in a more intelligent way? And it turns out that we actually found very interesting things that you can do. And Opti is not going to be it's not going to be a cascades optimizer like you see in the wild. It's going to be something very unique, with a completely tunable exploration search. So you don't
Mhm.
just plug in your cost model, but you can also effectively plug in the way you actually explore the search space. And exploring the search space is, such a big component of why, query optimization is hard. Uh, and that's usually where heuristics come into place, right? Um, since you just can't enumerate everything, you just hard code a bunch of heuristics, and both heuristics to guide the search process, but also heuristics that will simply transform your plan into what's usually something that's great to do. For example, filter pushdown, right? You kind of want to reduce the cardinality of your, that you get at each stage of your plan execution. So if you just push down a bunch of predicates, usually, but not always, it's a good idea. But writing a bunch of heuristics is also a nightmare in the industry, right? So what's happening right now, even like for very mature systems, is they write a bunch of heuristics, and then if a specific client has enough money and realizes that they have a query that runs very slowly, well, they would just copy paste it, send it to the engineers, at the company, and then they would like actually have to troubleshoot, go over the query, understand what's going on. Um, so yeah, with Opti, we kind of try to. It's like still an open research project, right? So we're trying to tackle a bunch of problems, also making it more performant. Cascades, the way it's designed, the framework is not very parallel friendly. Microsoft recently released a book about query optimization where they go over like how Cascades and their query optimizer works, but it's not always easy, to see how you could extract parallelism out of that, which nowadays is really important, since we've reached like the end of Moore's law, and we still want to be able to optimize multiple queries at the same time. So that's like one challenge that we want to address: performance. Better search space exploration, like I said. Better explainability. So if you're like a software engineer, let's say at Microsoft, and you get a query that like, a big query from a customer that, has run very slowly, well, you can kind of know precisely what rules have been applied in what order, and then you can kind of understand why you got, a poor execution time. And then also extensibility. Like we want to make it very easy for people to, just like for Calcite, to come up with a system and just write a bunch of rules, and inherit also the rules that we've already written, so they don't have to reinvent the wheel every time. Um, yeah, I mean, I can get into the details of how we imagine,
Hmm.
how we try to solve kind of the limitations of Calcite. Um, Maybe I should spend a little bit more time on talking what Calcite is about. I don't know.
Yeah, I mean, I have a couple of questions there, but yeah, I think let's talk a bit more about Calcite first, and then I'll ask those questions.
So, like I said, Calcite is really this is right now the only practical extensible query optimizer out there that's widely adopted in the industry. So, before I say anything bad about Calcite and like all the cons, I should really acknowledge the amazing work they did. Right, it is such a time saver, right? If you just want to come up with some engine, you can just inherit like this gigantic bank of rules that has been written by Calcite, and all this engineering effort. So of course it's not perfect. Every time you create a dependency, you're always going to be stuck somewhere as you scale, but it gets you like 90% there. Calcite also was, so it was created like 10 years ago. It's written in Java, and at that time, many of the database systems that were getting created were written in Java. So they integrated with a bunch of these databases, and uh, it supports a bunch of of databases. Also, you can write like your own rules, even if you get a query plan that from heterogeneous data sources. So, for example, if you have like a Postgres instance and a DuckDB instance, you could like write a generic rule on Calcite that kind of uses these both data sources. So it's a very generic framework written in Java that allows you to write rules and perform cost-based search to get better plans for your system. Now, the way Calcite is kind of annoying and like hard to use is that you kind of it is really tedious to write rules. It is not very easy to write rules because
Hmm.
you actually have to write some Java code. You kind of have to access the internals of uh, like how Calcite represents plans. So you have to deal with like Java source code. As a matter of fact, we actually had 20 students here at Carnegie Mellon, as a task, like as part of a class project. Uh, they were supposed to uh, kind of replace the DuckDB optimizer and then plug it into Calcite and apply a bunch of rules so that they can improve the plans that were so we deactivated the optimizer of DuckDB and we replaced it with Calcite and we tried to improve the benchmarks. And they actually struggled a lot, right? And it really was not an easy experience. So Part of it is because this integration with Java, and I'm not saying it would be the same for like pretty much any language, right? So the way we're trying to solve this is to come up with a specific DSL, right? So domain specific language, where you can write your rules in a very high level language. That's much easier to to write. And there's kind of like two motivations to do this, or maybe three. The first one is, if we go back to the example of Calcite, well, Calcite has around 200 rules in their bank, and on average, a rule is written in like 100 lines of code of Java. So that's like 20,000 lines of Java code. So that's like a lot of code that can potentially go wrong, and these rules can like clash with each other, meaning that you can reach like an inconsistent state. It's really hard to debug. So if you write a DSL, which is what we're doing with the Opti project, you can start doing some static analysis and check, if your rules do not clash with each other. So that's one reason to do it. The second reason is just easier to write, right? Like when writing rules, you kind of want to do some pattern matching, right? You want to match some patterns, you want to match some predicates, and then transform these predicates. Doing that in Java, I think Java recently introduced pattern matching, but it's still not the same as if you have like a specific dedicated language, to do this. So we believe it's going to be easier. It's because it's like domain specific restricted. So you don't have to, you don't bring the whole Java ecosystem. Yeah. Thirdly, the actual expressibility you get in Calcite is much less than what we want to support in Opti. So in Calcite, you can only write rules that are finite deep, right? Finitely
Hmm.
recursive. So you can, for example, match like 3 levels deep on your query plan, but you cannot write recursive Turing complete rules, right? So the matching engine and the transformation engine is not Turing complete.
Hmm.
Now, of course, this is both an advantage because you if you don't make it Turing complete, you don't have as high chance of you doing some weird things. But it's also, and we really believe this, it's going to limit the expressibility of so many interesting rules you can do. And I'm going to give a very simple example of this, right?
Hmm.
So let's say you have 100 joins, right? That's a lot of joins. If you just have a bunch of simple rules that just like commute each side, like A join B becomes B join A, and then join associative, that like just change the associativity of A join B join C. I mean, you can technically, try all combinations, but if you have 100 joins, that's going to take you so much time. So if you can write one rule that kind of like unnests all these joins into one multi-join, and then you kind of create this hypergraph of joins, and then kind of immediately get the sublines that you want to explore in one step. I mean, it's just a performance gain, and also you can like actually write rules that are also heuristics, right? So right now there's this separation that, okay, there's these cascades rules, which are, these very simple rules that just swap, for example, the commutativity of a joiner that just pushes down a filter one layer deep. Well, if you make your engine, your matching engine, Turing complete, which is what we did in Opti, then you kind of lose this boundary between heuristic rewrites and cost-based rewrites. So we're very bullish on this idea.
Interesting. You have mentioned so many like different and interesting points, and I want to make sure that myself and our viewers understand it, can relate it to some examples, right? So we talked about like starting with cost model, and which is a function of having some inputs, and will give you like how much this cost is for a certain query. And then the second problem you mentioned is the search space itself, right? Because there are like n number of combinations and permutations that you can run your query differently. And that also depends on a lot of inputs, right? Like you mentioned heuristics and uh, rules based on top of it. So let's take some examples of these rules. So I know you mentioned about if you have 100 joins, right? But let's take like a practical example. I don't know. Let's say I have an employees table or something, and I want to join it with I don't know, salaries table. So in a simple example like this, and I want to join them based on I don't know, employee ID, and then I want to figure out like group them based on the salary bands and so on. So this is like a basic query, one join maybe and some aggregation. So what would rule mean in this particular example?
Right. So the way you would write a rule is like you get an input logical plan, right? So you get a binding. For example, and this is really agnostic to what the underlying table is, right? So you would represent the department table by at one point it would become like get access that data that sits in some table,
Mm-hmm.
right? Um, and the first thing that the database does, right, is to create a first initial plan, this logical relational plan. And writing rules means matching on this on given plans and then creating new plans out of that are equivalent. So for example, if the query that you just mentioned is like, for example, joining the departments with the salaries, well, you could first go over all the departments and then join with the salaries, or you could first go over all the salaries and then join with the departments, right? So how it would translate in a role is you define your operator, your logical operator. There's going to be a join, and then the role is going to output the same join but with the children swapped, right? So this is an example of what a role would look like. Now this only tackles what we call logical to logical transformations,
Mm-hmm.
but then what makes cost-based query optimization in databases very hard is that you actually have you need to transform this logical plan into a physical plan at one point, and
Okay.
these are defined as implementation rules. So implementation rules are you get a logical plan in. For example, just getting the departments table, and this is at a very high level, right? But then it needs to get transformed into either an index scan or like a table, like just a normal table scan, right? Let's say the original query wanted to get all the employees that were sorted by their age, right? If you have an index that has like a B plus tree on the salaries of the employees, then you
Mm-hmm.
can just scan on that B plus tree directly versus scanning on the base table and then having to reorder and like apply an ordering algorithm on top of that.
Mm-hmm.
So a simple rule like that, would be okay. We have get x, where x is pretty much any table, like any logical child, right? And you want it to be ordered according to certain properties, right? And then a rule would be like, okay, let's check if I have an index in my catalog. Yes, then I can do an index scan, for example, right? So you write a bunch of rules that like kind of um, has to support all the possible mm, uh, ways you can execute your query, right?
Mm-hmm.
And that's where it gets hard, right? Because you cannot, like, people can come up with like a lot of crazy queries, right? Like you cannot know in advance what kind of queries they will come up with, right? So you have to write rules that are generic and that will kind of compose with each other. And this is really this exploration phase that I was talking about, right? Like you need to know the order in which you're applying the rules, and this makes all the difference, right? Like I can express all the rules, but if I do not know the order in which I apply these rules, I will never reach to an end, right? Um,
Right.
I hope that clarified it
That
a
that
little
makes
bit.
sense, and that's a good explanation, at least for that simple example. And like I can imagine there can be like so many variables, depending on which your result may be entirely different, right? Like I've seen cases when there was an index on a column, but then still the database decided to not use the index, right? Or in some cases, the table would be so small that it's entirely in memory. As you took an example of already sorted columns, then there could be like data skew where for bunch of let's say employees, there are just ton of data, and for the other employees there is not too many data. So cardinality issues and stuff like that. So there are like so many variables that makes this search space even large
Yes,
and
absolutely.
more complicated, as you mentioned. So
And it's not just I mean, it's not just in terms of like, the physical plans you can output. It's also the if you have a distributed database, right, then you
hmm,
need to take into account like network latencies,
right.
um, network partitioning. Like, if your data is partitioned in certain nodes, you also have to take into account data layouts, right? Like maybe you're using something that's like both has that represents your data in rows and then represents your data in columns, right? So you might have to decide on that.
Hmm,
And coming up with the right abstractions inside, like within one extensible core optimizer, is really the challenge. One of the challenges we're trying to solve, right? So that you get this really this framework where you can like define the properties of your database, where you can define all the operators, and then write rules that kind of interacts, kind of like defines how you the equivalencies, within your entire search space, and then also deciding how you actually apply all these rules in what order.
right.
So that's why I mean, core optimization is considered to be an NP hard problem, right? Because there's
Yeah,
just so many variables. It's so hard.
right. That makes sense. How do we, so writing a rule, right? Like, how do we come up with all these rules? Like, even so, let's say Calcite has like, I don't know, 200, you mentioned
I
rules.
believe it's around there. Yeah.
Yeah. So how do we write this tool? Like, what is the process of writing rules? If I have to write a new rule, for example, add something to Calcite, what are the parameters? What are the different approaches do I have to take to make sure that the rule I'm writing makes sense? Um, does that make sense?
Yeah. Yeah, no, absolutely. So in for Calcite specifically, they use inheritance, right? So you would create a new operator that extends like this generic operator.
Hmm.
Then you can add a bunch of data into it, and then you have this unmatch function, right? So when this subplan matches your operator, then you know output and transform it as follows, and then you just output some vector, for example.
Hmm.
So that's how it works in Calcite. In our DSL, it's going to be similar, although more user friendly, like I
Hmm.
said before, because you're not writing in like Java. You're actually writing into a specific DSL where you have all the supports for all systems properties, physical properties, and all these things.
Yeah.
Um, and then how do you know if you break something? Well, that's why the students at CMU were struggling so much, right?
Okay.
Because indeed, it's you can write a rule that doesn't interact very well with another rule, and then you end up applying like cycles and doing loops, right? An
Hmm.
example of that is like, let's say I write a rule, and I'm just going to simplify it for the viewers. Like, let's
Yeah.
say you have 1 = 1 + 0. It's a rule, right? Now 1 + 0 can that one inside that 1 + 0 can be re-expanded into a 1 + 0. So
Hmm.
in reality, you have 1 + 0 = 1 + 0, and then an infinity of zeros, right? So you need to be careful that you do not end up with in like a loop, right?
Yeah.
And that's actually something that can happen in Calcite. Like you can actually start running, and then you just loop forever,
Hmm.
and you have to troubleshoot that, and then you realize that the rule that you've written is doesn't interact properly with the other rule, right? That's
Very
why it's just
interesting.
such a hairy process right now.
Right. Yeah, so I think you mentioned another point about specifically comparing call side, right? So you have like this Java interface where you have to write Java rules, and then like people who are used to writing Java is still fine, but you mentioned a couple of limitations, right? Like first, you may end up in this kind of infinite loop, and writing let's say recursive rules is not really possible. It can go at least like, I don't know, 2 3 level deep. That was another point that you mentioned. So from an interface perspective, I think having a domain specific language makes a lot of sense because it will be optimized for that particular use case. And then you don't need to have like Java experience, for example. If you understand the domain specific language, it's well and good. I want to understand, as you mentioned, it's written in Rust, like Opti is written in Rust. What specific advantages did Rust bring to you? Like we all know by this time that Rust is memory safe. It's like highly performant. But what specific advantages does a language like Rust bring to a project like Query Optimizer?
Yeah, that's actually a great question. So Originally, there was some people wanted to do the project in C++, but mostly because people at CMU were more comfortable with C++. Um, Now, the way we've started to write C++, at Carnegie Mellon was using so many macros that, to get like safety, that at the end it kind of, justified itself to use Rust. So this is really, why we chose Rust, because, it had to be a systems programming language,
Yeah.
because you want it to be performant, like you said. And, we were kind of having all these macros with C++. So, we just decided to all learn Rust and write it in Rust. So another reason is also data fusion, right?
Hmm.
So data fusion would benefit actually a lot from a query optimizer. So right now it's just heuristic based. So it also made a sense from that perspective,
Hmm.
right? Um, so that we can kind of like I mean, I think overall, like most open source projects, like Velox, Spark, would benefit from Opti, right? Because these are like open source projects that are usually backed with, by some companies behind them. But the companies, they have a lot of money that they're paying a lot of they're paying a lot of money to these people that like are responsible to optimizing, the queries. But unfortunately, it's not open source, right? Um, so data fusion is kind of in this situation where they would benefit a lot from a cost-based query optimizer. So the integration with data fusion is, one motivation. Now, in terms of like software engineering, we found out that I guess like the question is like versus other high-level languages, right? Like for example,
Right.
Scala and these things. Um, I guess it would honestly be easier to write it in like a much higher level language, right?
Hmm.
It's just going to be performance that's going to hurt us at the
Yeah.
end, I believe. So, I mean, the functionality that are really useful, like in Rust, are stuff like, pattern matching.
Hmm.
You don't have to deal with inheritance. They have like these really nice enum types. Memory safety, of course, but like even that aside, like let's say, memory safety was not a thing. I believe Rust is a really expressible language. Also, in terms of how it handles the concurrency aspect, we were pleasantly surprised how easy that was.
Hmm.
To just oh yes, coroutines. That's also something that we found out to be very 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 useful. So so Rust has this has Tokyo, right, which is uh, this coroutine library that you can use, and we use it extensively
Hmm.
in our optimizer because we kind of divide the optimization process into a bunch of small jobs, and then we execute these small jobs into coroutines. So you can spawn like hundreds and tens of thousands of coroutines, and then the challenge is in what way do you schedule these jobs, and like defining what order you execute these jobs is pretty much going to reduce us into what's your exploration.
Hmm.
How are you exploring, your search space? So I would say for that it was really really useful. Now, of course, you could probably use the same thing, in Scala or like in Java. Um, uh, Although I have not used coroutines that much in on the GVM, so
Hmm.
I don't know how it works there.
Yeah.
Mm.
I mean, it's better than the previous world of having no virtual threads or coroutines, for example. But I also don't know how it compares with Rust, to be honest. But yeah, I mean, Rust makes total sense. It's a first class systems programming language. So yeah,
Mhm.
that makes sense.
Also, it's
Um,
really kind of like rising in popularity right now.
right,
It's kind of the hot language,
right.
like Java used to be,
Yeah.
15 years ago. So also from that perspective,
Mhm.
you want the cool kids to be interested into the project.
That makes sense. That's a pretty strong point, to be honest. Um, okay, I think so. We have covered like and kind of explored the problem space, what exactly we are trying to solve, and there are a lot of problems I didn't actually imagine, right? So like user interface is a big problem. Like if you want to integrate a query optimizer, it has to be easy. And you gave like a case study of CMU, right? Students struggled a lot to kind of integrate Apache Calcite in DuckDB. The other one is not fully utilizing the hardware or not fully optimizing the workloads. um, and some other points around, extensibility. What if you have like a distributed database and you want to have a query optimizer? So there are like bunch of use cases and features of Opti. So I think it's time that we get into what is Opti, and in terms of how it works. But I want to draw a picture of, like a very high level picture for our viewers, so they can sort of create a mental model of what exactly is happening, right? So I write a query, and then that query is, goes to the, let's say it has a like a logical plan, and then it goes to the optimizer, and it's then creating a physical plan, and so on, right? So in general, talking about two types, let's say two classes of databases, right? Like one is the like monolithic databases where it's just one database, and then there is distributed database where data is distributed, partitioned, and networked, or multiple nodes exist, and so on. So where does this optimization take place in both the worlds, and how different it is, if we have to kind of plug something like Opti?
Yeah. So we believe that we should first tackle it from a centralized perspective, right? So you mentioned distributed queries. Well, we believe that like the challenges involved in distributed queries are very similar than the challenges you face on a central, like monolithic system.
Yeah.
Like the only thing that you add in a distributed system is the network, pretty much, right? So you can logically represent your distributed system as like one logical system, right?
Yeah.
So, and then of course, like the optimization that you're going to apply might involve the characteristics of your network, right? If you know that the data is on a specific node, then you might want to execute a part of that query locally, right? And then only output part of the result to some central node. But from like we don't believe it's going to like this distributed versus not distributed is going to change the approach and how we do query optimization. Now, in terms of how it would how the flow would be, well, people write a first the SQL query, and then it gets you know like a first plan gets created, right?
Right.
And this is the logical plan that we ingest into our centralized single threaded. I'm going to specify this because I mentioned the coroutines, but for now the logical plan that we're going to ingest is in a system that's single threaded, and it's going to create a task, right? A task to optimize that that query, right? And in the meantime, like a bunch of other clients can optimize queries. So you get like a bunch of parallelism between different queries. So what happens when the system creates a task to optimize a query? Well, it will launch a bunch of jobs that will start applying rules, right? And these jobs all get like scheduled inside a big queue. And the order in which you apply these, so these jobs, are executed in coroutines, right, in parallel, right? But the order in which you execute these jobs is going to determine what your search space exploration, like how you explore the search space, looks like, right? And so going back to how the interface looks like, so you you optimize, you request for an optimization, it creates a task, that task generates jobs, these jobs gets executed, and as soon as a physical plan gets generated, it gets returned back through a channel to the client. And this channel remains open as long as better plans keep coming in. And this is really a unique feature of Opti, right? Like it's kind of a streaming model. Like I try to give you a plan as fast as I can so that you can like start executing it. But if something better comes up, then I will notify you. I will keep telling you when better plans come, right? And this is really interesting from a research perspective because you can start doing stuff like, you start executing your plan immediately, right? Or maybe you just wait 10 milliseconds. You wait 10 milliseconds because the user is not going to notice like a 10 millisecond latency depending on certain kinds of application. You get the best plan you have in that 10 millisecond time frame, and then you launch your execution engine. You start executing the query, right?
Hmm.
And while you do that, the query optimizer is still trying to find better jobs. It's still trying to find better plans, right?
Hmm.
And if it finds something better, then the execution engine can like interrupt and execute the other plan. And you can start being really like fancy about it. Like you can, while the execution engine is like executing the first instance of the plan, it might feedback to the optimizer and tell the optimizer, hey, I just sampled this table, and this table has a selectivity that's very low when you apply that predicate. So I can refine my cost model while I optimize a query and while I execute it. So there's a bunch of interesting things you can do with that streaming design.
That's interesting. And I want to make sure we all understand that a bit more, right? So it's a streaming model, as in, as soon as a single plan is ready, it is served to the client. The client may decide to wait or may start executing on the plan. And then if it
Absolutely.
has feedback, as you mentioned about the selectivity of on a certain column, then it can give you that feedback and you can update the cost model, right? So
Exactly. So the
what?
optimizer can like refine. Mhm.
Right, right. So it's like a two-way thing, right? Like you give me a plan, and then I also give you feedback, so you can give me more plans, right?
Exactly.
So I have a couple of questions there. One, when we say client, what client is it exactly? And the other question is, what happens if you give the client a new plan that, hey, there's a better plan available? What happens to if the client is already executing certain query? Is that cancelled? It depends on the client, or yeah.
Okay. So first question, what do we define with a client? A client is anything that subscribes to an optimization process, right?
Hmm.
So typically you can think of that being the scheduler of like the execution engine,
Yeah.
right? So now, what do you do when you get a new better plan and you're already executing a plan? Well, this really depends on the application, right?
Hmm.
So it really kind of depends on each scenario. So if the plan that you're executing had like an estimated time budget of like, I don't know, 100 milliseconds, and then you get a new plan that's like, I don't know, supposed to take 70 milliseconds, but you've already been executing that first plan for 50 milliseconds, then maybe you don't need to interrupt it, right? But
Hmm.
if you've launched the first plan, it's supposed to take like 2 hours or 3 hours, and then you get something new that's supposed to be running like 10 minutes, which is completely possible, right?
Hmm.
Maybe in that case, depending on how many resources you have, you might just launch both of them in parallel or like just
Hmm.
stop executing another one. So all these decisions are really made at the level of the execution engine, right?
Makes sense. So if so, as a mental model, let's say on the client side, right? Like, how do I decide if I should wait for more query plans or I should just start executing? I think a good rule could be that if the query is already going to take like 2 hours, maybe it's worth waiting few milliseconds more to get a better plan. Or if it's like already going to be executed within, let's say, a few milliseconds, then it's best to just execute it and not wait those many milliseconds, right? So I think
Absolutely.
it depends a lot. Again, there's a lot of variability. Like things can go wrong. Like a client can start executing, but hey, there is a better plan, which has a way better latency. It can always happen. So is there like a memory to it where oh, I made this decision, but it was kind of wrong, I should have waited longer? Is there that kind of model where you keep improving based on the communication that has already happened between the optimizer and the client?
So you mean like a system that adapts as it goes, like that kind of learns
Right.
from the past? Yeah, no, absolutely. This is something that's completely possible. Now, it would be, I would argue, it's a more complicated way of
Hmm.
achieving it, but it's completely possible, right?
Right.
And this kind of transitions very well with the other big implementation specifics of our system,
Yeah.
which is persistent memoization, right?
Hmm.
So we share like our optimizer is pretty much building a database just for query optimization, right? But the queries are just optimize this, optimize that, right? So we log everything. We store all the intermediate results so we can reuse it for other queries, right? Other queries can reuse the same exploration space. And we log everything. Like we log what rules have happened at what time. And this kind of allows you to mine data, right? You can kind of figure out and learn stuff like, hey, I realize that when I apply these rules, I often get great plans. So maybe I should do that more. And you can start having like reinforcement learning things, right? Like you kind of have the system learn as it goes. Now, I would say though, I mean, it sounds really cool, right? I mean, adding AI,
Yeah.
can get you great results. However, it kind of makes you lose understandability, right? As soon as you add stuff like reinforcement learning or like language models or whatever in your system, you kind of lose explainability because you don't no longer know why a certain thing has happened. So that's why we're seeing in the industry kind of less and less black box AI. But once again, this is something that we are really looking forward to explore, right? To see how much, like, if we do something like you just mentioned, right, that you just suggested, how much better can we make our database, right? So
Right.
these are all very interesting questions.
Perfect. Let's go to the next point, right? Like you mentioned, so from the applications perspective, when I want to integrate with Opti, I think it's clear that I have to make certain decisions and, I have to keep improving it. But then, let's say I give you a query plan. What exactly, like, so you mentioned there are like queues and, you create coroutines, and each of those coroutines will is try to execute a different path, try to, figure out a search space and so on. um, what is the limit to that? Like, how do you start that? Okay, how big is the search space, right? And how many threads I have to create, uh, and so on. How does that process get triggered?
Yeah, no, absolutely. So right now, every time there's a new, so that's what we call, in the jargon of query optimization, a fork point, right? So when you realize that you can go two directions, right? Either you explore, you go like you take the left path or you take the right path, right? And deciding, whether, for example, you just schedule both paths into like two threads, or whether you just do not explore any of them and you just prune, you just stop exploring that path, or whether you just do one and then the other, or the other and then and then the first one, is all going to result to a scheduling problem, right? So we want to make the scheduler programmable, right? So that you can write rules based on like how do I want my rules to be applied in what order. And so Microsoft has this, like they call this concept guidance and promise. So a specific example of that is, for example, Cartesian products are usually bad, right? Unless there's like specific scenarios, I do not want to apply a rule that's going to transform me my plan into a Cartesian product, right? So every time before you schedule something, you would check, hey, should I schedule this? Is this part of my scheduling policy? If yes, then you just execute it. And then also, when I say execute, just imagine you have like a bunch of threads available, right? It's just a big thread pool, right? So we just abstract that problem away. But still, like whether you decide to execute a job or not is very relevant, right? And there's kind of two ways of approaching the problem, right? The first one is just write heuristics everywhere, which is what promise and guidance is about, right? For the Microsoft, that's how the Microsoft people define it in the book they recently released about query optimization. And the other approach is like to just throw ML at it, right? To just throw some reinforcement learning, which is what has been done by some folks over at Berkeley. Um, uh, and then you can get like some great average performance time. I mean, great average results on average. But you do not, you kind of lose explainability, right? You can find that specific query that completely breaks your system, and it's really hard to patch, right? Because you cannot just like change the weights in your machine learning model. So that's why we kind of believe the scheduling problem is going to be hybrid. Probably you can use AI to get like 90% of the queries to kind of like find the common patterns, but then having an ability that you can actually hard code the rules is going to be very valuable in the industry.
That makes sense. Um, how does the query optimizer understand that it is not taking more time than the actual query execution would take? For example, I write a query and that probably would take, let's say, 100 millisecond. I mean, depending on the type of query I have and data I have. And let's say the query optimizer takes 50 milliseconds. So to achieve that, or even more, like close to 100 millisecond. So how does that know? The query optimizer knows that the query execution itself is really cheap. So I don't have to kind of explore the entire problem space. Um, you know what I'm saying, or
Yeah, no, absolutely. I
okay?
believe this kind of relates to this subscriber model, right?
Hmm.
So in advance, you cannot really know if the plan is going to take a lot of time to explore or not. So that's
Right.
probably where you can start doing some simple heuristics. For example, the optimizer. The good thing about our optimizer is that it produces plans, like initial plans, much faster than anything else we have, in the industry. This is because we've like changed and tweaked the way the exploration actually happens. But I don't want to get too much into that because it's really going deep into like how cascades work and these things. But anyways, so you get a bunch of plans like you can execute, and then if you see that the first plan you get is supposed to run in 10 milliseconds, then you just run that immediately, right?
Mm.
Because it's just 10 milliseconds.
Right.
However, if you get something that's like 2 hours, then maybe you should wait like I would say 100 milliseconds, right, to see if the optimizer can come up with something better.
Hmm.
I think executing it directly is probably not the good option because maybe the optimizer comes up with a plan that only takes 1 second afterwards, right? So you don't want to do that either. But the optimizer could be wrong, right? The cost model could be off. So sometimes it might be good to execute the plan initially because maybe a plan that's advertised to only to take 2 hours might end up taking 1 minute, right? So it's like there's no definitive answer on this.
Yeah.
I what I imagine, and this all depends on like the how the client is implemented, right? But you usually wait like I don't know 50 to 100 milliseconds because that's the time that a human would not even notice a difference, right? And then you just launch an initial execution job, and then you just wait and see whatever new is happening. Now, this is actually very similar to what Umbra is doing.
Hmm.
So the German database. So not for the optimizer, but for the compilation process, right? So Umbra is this very interesting database that kind of produces code that's going to be run um, instead of like interpreting the plan, right? And Umbra has these three types of execution modes. So the first thing that it does is like optimizing, like compiling, your query plan and producing code, but like with not a lot of optimization passes, right? So that you produce that thing really quickly, right? Because you don't want the compiler to become a bottleneck, right? Like imagine
Mm.
you have a query that only is supposed to run 5 milliseconds. If you're invoking GCC and compiling that plan takes like 100 milliseconds. I mean, that's just very bad, right?
Mm.
So they have like Umbra has I think three execution modes. It starts with the first one, like it assumes that it's going to be fast. If it realizes that it's taking too much time, then it compiles the query like with an additional optimization mode. And if that's not sufficient, then it does like a last thing, and then it invokes the heavy machinery. So we can imagine something similar here, right? Like you start executing the first plan immediately, and then if you realize that it's taking too much time, then you might cancel it and start another one or have two in parallel. Yeah.
Interesting. Yeah, that's interesting. And again, there's no definite answer. It has to be,
Mhm.
like a feedback loop. And you can subscribe, keep yourself subscribed to the new query plans, and probably learn from it. You mentioned that. So let's take, let's go slightly more deeper, right? So once you have the query plan, you have these coroutines, and they take the task of exploring the space. And you mentioned that you memoize everything in a persistent storage, right? Where does that exist? Like, for example, I want to plug Opti into Postgres or something, right? And where that storage is configured, and how that is laid out, and how that storage really helps you. And like, is it like a shared storage across all queries, or like separate storage and so on?
Yeah, it could be. It could really be anything, right?
Mm-hmm.
So across all queries, yes. I mean, there's two things of it, right? Yes, this memo storage layer is shared across all queries, right? Across all clients. However, it can be like disaggregated. The storage can be disaggregated. Like it can use any database. We're right now we're just defining this storage layer as just an interface that you have to comply with. So our initial plan, for development purposes, is to just have something in memory. But we have plans in the incoming months to actually add a SQLite backend, right? So you actually you can like restart your database. You get like error recovery. You get like failure recovery. You get transactions and all these nice features that we have, from databases. Um, but really, like it could be, any it could be a Postgres instance. It could be,
Mm-hmm.
or even maybe later we will come up with our own storage layer, right? Um, that being said, like using something like SQLite offers us the advantage of actually being able to query it with SQL, right? Like
Mm-hmm.
I can query my own optimizer, right? Like you can write something like, hey, select all the queries that have taken mode at that time. What
Mm-hmm.
is the most popular rule? So it kind of, that's what I was saying. You can like mine data from
Right.
your optimizer.
That's really powerful because right now it's not really possible to kind of understand what's going on, right? Like what's
Yeah,
going on in
exactly.
the
Yeah, yeah, yeah.
optimizer, right?
Especially if
S-
you're, one of these engineers that has to, understand why a specific plan was,
Hmm.
took so much time. Well, if
Right.
you can query it and it just keeps track of everything,
Hmm.
I mean, it's just so much easier.
So it gives you like this native observability as well. Like if you want to really go deep, understand how things are working, why things are not working,
Yes,
you can go
it
just query
gives
the
you
database.
explainability and also gives you like a cache, right?
Hmm.
You can reuse previous results. So, for example,
Right.
if I've already optimized this plan in the past, which like most queries are like queries that we've seen in the past, right? I mean, so if you can cache that,
Right.
I mean, you just save time.
Right.
You don't have to do it again.
Absolutely. That's so cool. I want to understand. So you mentioned that like apart from these coroutines and tasks and queues and subscription model, what other optimizations are done that makes it really fast to kind of explore the search space and apply these rules and figure out what is the best plan possible.
So I think right now it's kind of hard to say, given that the project is still under development. So
Hmm.
we kind of expect having something like a prototype in a month. Uh,
Hmm.
that time we're going to benchmark the system and try to find where the bottleneck is. Um, One of the big advantages, like I said, is that we define like coroutines, so you can like really, we get a bunch of parallelism. So that's going to be great. However, one bottleneck that I see the system having in the near future is its reliance on the rule engine. So let me maybe just explain, how that part of the system works. So whenever you're writing, a rule in the DSL, right, it is going to be compiled and transformed into, an intermediate representation that the exploration engine can then use and apply rules on. However, the plan, like this exploration process, this DSL is interpreted, right? So it is not generating code that is then getting executed like a normal
Hmm.
compiler would do. So right now we took the decision to first interpret the execution of the rules. So I believe this is going to be a bottleneck, and it's something that we would look into later on to actually code-gen the rule in Rust, and
Hmm.
then actually link that and execute that part in Rust. So uh, this is kind of like a hypothetical optimization, but we have to see, for sure, to find out, where the bottleneck is.
Hmm.
Now, in terms of other optimizations, yes, I just remembered of one, which is quite interesting. So, and this is kind of related to the memo, which kind of caches, all the intermediate results. Um, if your system crashes and then goes back online, you do not have to reapply all your rules to reach back to specific states. So we implement kind of this notion of checkpointing just to make it like clear It's not exactly checkpoints, but it kind of looks like checkpointing. So you can restart the execution of rules at specific times rather than like restarting the whole rule, right? So imagine you have like your entire exploration process where you can have like a bunch of checkpoints in there where you can restart the exploration from that specific point rather than rederiving the whole thing since the beginning. So that's something that we are actively trying to implement in the system, and we're really like excited about that.
Right. And that basically reduces the entire problem space because you're starting at a specific snapshot and not doing all the
Exactly.
preliminary
Yes.
steps, right? Sounds
Yes.
cool. Okay. You mentioned about the feedback that you get from the application, right? Like, hey, this query plan executed in 10 seconds, for example, but the optimizer said it will execute in, I don't know, 100 millisecond. So is there only these feedback when it's, let's say, a negative feedback, or you also get positive feedback in the sense, oh, this query actually ran within the estimation that was given, and then you also memoize that to get like, okay, this actually worked, or only the negative ones?
Yeah, no, everything,
Okay.
everything, right? So if you get something that, I think one of the things I'm the most, bullish on is right cost models. Cost
Hmm.
models are very brittle right now. It's a massive research problem.
Hmm.
Um, because the source of truth is going to be the engine, right? How much time did it take the engine to actually execute that query? So
Right.
if you can match the estimate with the effective cost and then kind of improve that over time as you get more and more data,
Hmm.
that's something we can do. Now, whether once again you apply machine learning techniques or whether you apply other kind of techniques, this remains to be seen, right? But once again, providing the framework, like providing a system where you can do these kind of things, will allow like it kind of creates this research playground for people in the industry, people in academia to just experiment on and see like, hey,
Right.
what can we do? So like these are ideas that I think would be very interesting to explore, and they've already been explored to some degree in the past. This thing about like comparing the effective cost and the cost estimate,
Mhm.
but coming up with like an open source system that everyone can use just makes it much more concrete and less
Right.
hypothetical.
Right. That makes sense. I want to understand a bit more on the cost model side. So when we say cost model, right? So you mentioned that it's a function that gives you some estimate of the cost, right? And what are the different inputs to that function that derives the cost, right? Like, we can imagine that there are so many, but let's talk about some examples.
Yeah, no, that's a very that's a great question, because I believe it is like a big open question in research.
Yeah.
Um, Typically, when you look at like the traditional systems, the inputs of the cost model is going to be your statistics, right? So systems like Postgres, they sample a bunch of statistics. They create histograms on your table to kind of like get the selectivity of your data. They estimate a number of distinct elements that you have in a table, which is going to be relevant when you do joins. They also try to come up like they try to estimate the most common values in that you have in your data set,
Hmm.
and then you use these base statistics, right? And every time you have an operator in your plan, you are going to make an estimate of how like what the cardinality is going to look like, right? And I think Postgres really has like this almost textbook approach of cost models, meaning that you take the base table statistics. If you are if you actually are estimating the cardinality of a base operator, for example, a scan, and then as you go up in the query plan and you want to like estimate the cardinalities, for example, of the first join, you would take the cardinality of the left side, the cardinality of the right side, and then apply some magic formula that assumes, for example, data independence, right? So if you know that you had a selectivity of like 50% and then a selectivity of 1%, and you do a join, right? And like you have an AND operator, right? Like you want to have both. You just assume data independence, and you just get the new cardinality. So these systems are not great. They're not great because they're extremely brittle. Uh, and one example of that is like, let's say I have two columns in my database. One is like, the car brand, and then the second column is like the nationality of that car brand. So I would have Tesla and then United States, and then I would have Toyota and Japan, right?
Hmm.
Well, you have a lot of correlation there, right? If you know that you have a Toyota car, well, then it has to be Japan, right? And so these kind of very simple examples completely break, state of the art cost models. So there's a bunch of approaches right now, in the literature trying to get better cardinality estimations. So one very popular approach, also pushed forward by Berkeley, was to use machine learning, right? To just use I think, like, if the viewers are interested, it's called the NeuroCart paper, where they kind of try to estimate the cardinality with just an ML model. Um, but once again, I mean, we have at CMU, our concerns about machine learning. We think it's great, but it's just like a little bit, right? Because if you completely lose the understandability of your system, no one's going to use it. Um, so we are very interested in seeing, okay, how can we modernize cost models as well? And something that we experimented last year when I originally joined the Opti project was to do something that's called statistics propagation, right? So you have the statistics of your base tables, and then instead of just using the cardinality of that first node and then applying these bizarre rules, you kind of propagate your statistics as you go up in your query plan while you're estimating your query plan. So when I say as you go up, estimating as you go up in the query plan, this is because the way you cost a plan is by doing it bottom up, right? In case some people are confused. You would start like, how much cardinality do I have at, the bottom layer? And then, every time you go up, it's like this recursive algorithm
Right.
to estimate the cost of the cardinality. But so yeah, if you can actually keep the statistics alive at each node, then you do not make these mistakes like I just showed you about the car brands. And no one knows this. I mean, there's no research about this yet. Using like new heuristics, new simple approaches to just modernize them, right, and see how much better we can do.
Very, very interesting. And as you said, there can be a lot of research that can be done in this area. And there are a couple of, like, in the entire discussion, there are a few papers and references that you mentioned. So I would add that in the description so viewers can, check it out. Um, Talking about like the challenges that you've faced so far, like what has been the most annoying challenge that you have faced while working on Opti?
I have to think about that one. um, I think it is learning all the different aspects that are involved in core optimization, right? Uh, it is core optimization is a very hard subject because first of all, you kind of have to understand how query execution works, right? So that's the first prerequisite.
Hmm.
Understand like the different ways that people execute queries, like the push-based, vectorized execution engines versus the compiled ones. Um, because at the end of the day, that's what the plans that you're trying to produce, right? So you need to understand this. Then you also need to understand, like you need to have a certain skill set in mathematics, and you need to understand, these algorithms, like the cascades algorithms, these volcano algorithms. You need to understand them very, very deeply, like exactly, why is this happening, and what is the recursive substructure of this problem, right? And then the last aspect is more PL, like programming language theory, right? So since we're building this DSL, which
Hmm.
wants to kind of improve the experience of writing rules, well, we're building a compiler, right? Like, so we have to build a compiler from scratch. So it's really not, I would not say it's like, oh, that's the hardest thing. No, it's kind of a sum of components.
Hmm.
And there's a lot of components to sum. And I believe that's why core optimization is so hard, because you have to find like a skill set in all of these components, right? You have to understand, like from a mathematical perspective, how these algorithms work. What are the trade-offs? You have to, actually implement it in like a systems language, right, to be performant. Then you have to write a compiler. So there's just this blend of problems that just create this one big problem. So it's a subset of small problems that create a bigger one, I would say.
Right. Yeah, that's a valid one. I mean, if you can't understand something, you cannot optimize it. Like
Absolutely.
understanding it is the first step, and then you can optimize. Oh, this is something where we can optimize. So that makes sense. You have briefly covered what's coming in the future, like what's your plan. But if you can, summarize, let's say, I don't know, some features or some things that you've been working on will be released soon. What are these?
So releasing soon, I think, will be data fusion, right? So we will be able for people that use data fusion, they will just like throw their catalog. We want to support Iceberg for now, so it's going to be Iceberg and data fusion, and then we just okay. Let me rethink this. Mm, like okay, I guess there's two answers to this question. So short term, we will want to support data fusion, right? So data fusion and like a catalog like Iceberg, so that you can optimize like pretty much all data fusion queries that do not involve updates or like that are like select join project queries, right? So we kind of want to, and also aggregates, like we want to reduce the scope in the immediate future to that, right? And then expand to more complex stuff like arbitrary subqueries to a later stage. So this is like in the immediate next 2 months, we want to release something that where you can just like some interface, some web interface where you can like connect your database and then get optimized rewritten data fusion queries, right? Now, further, in the let's say the next year, we want to really build like query optimization as a service. We want to integrate stuff like Substrate, right? So that it could support a bunch of other engines and not just data fusion. We want to support more like more input plans, like the Germans call it arbitrary query nesting, so that like you can have SQL queries inside SQL queries, and that would also produce good plans. Something else we want to tackle is cost models, like I mentioned. We want to go a bit deeper in that and see how we can build cost models that are more effective than like what we have right now with Postgres. Um, and really, like, yeah, having this service, right, that we can run and then gather data from the users
Mhm.
and then refine the system based on the data that we will have.
Yeah.
Yeah, I think that sums it up.
Yeah, so many interesting things, and really looking forward to it. So I wish you all the best for releasing all the features. I really looking forward to it, and thanks for
Thank you.
joining me today. And it was such a fun discussion. I learned a lot, and I'm really more curious about learning about query optimizations and so many things that I don't know. I'm just interested in learning that. So thanks a lot again, and in the future when Opti has probably, I don't know, later this year or next year, when it has released more features, probably we can talk about them as well.
Yeah,
So
no,
yeah.
absolutely. I'd be very happy to talk again about how the progress has been. It's still very early, right?
Yeah.
I mean, although we've originally started a year ago, but like I think it's only these last 3 months where really we have like fleshed out the design, started implementing, the entire code base. We're sitting right now at like 20,000 lines of Rust code, and we expect it to reach like 30, maybe 40,000 lines of code before we actually have like a solid prototype. And then, I mean, it is a really big project, right?
Right.
And we really hope that we get like open source contributions to it, and people writing connectors later on, so that they can support their own database engine. And yeah, it's really we look forward to that. It was great being here. Enjoyed it a
Awesome.
lot. Thank you.
Yeah. Then have a good one.